All right, let's get started. So what's the overview and agenda for today? Basically, first thing we want to talk about is why is this foundational information so important, right? That's the first thing. Then we'll talk about the basics of TCP/IP protocol suite. What is it? What is it made up of, and so on. And we'll talk about some of the basics of the main protocols: IP, TCP, UDP. We'll go briefly over some of the other core protocols. We'll also talk about the basics of routing and TCP/IP and subnetting. IPv6, of course, has to be mentioned. And finally, we'll have time for some Q&A. Yeah. So that's the agenda for today. Hope this is of value to you guys, and it's a good use of your time. Now, first thing is, why do we need to know this? Well, guess what? TCP/IP is quote-unquote the main protocol used today in pretty much everything, right? That's why it's a universally used protocol. We use it at home, by the way. We use it at work. Most of us use it at work, right? There are other protocols that are used, but they are very specialized for very specific purposes. But by and large, whenever we are communicating on the internet, in our networks, printing files, accessing files from our servers, performing database operations, all that is using typically, almost always, it's using TCP/IP. So without this knowledge, all technical professionals can't really design, operate, or manage, or even troubleshoot networks. These days, even non-networking professionals like DBAs, database administrators, programmers, developers need to have a reasonable understanding of TCP/IP for these reasons, right? So that's the big thing. And it's remarkable. It's astonishing. It's amazing how often even networking and desktop support, by the way, help desk support, networking professionals aren't always as knowledgeable on TCP/IP as they should be, ideally, right? So that's the idea there. Now, what is TCP/IP? By the way, in classes when I teach, if I ask students what is TCP/IP, I specifically warn them. I tell them, don't tell me it's Transmission Control Protocol, Internet Protocol. I already know what the acronym stands for. I want to know what it is. In fact, I tell them that if you tell me it's Transmission Control Protocol, I'm going to even ask you, is it manual or automatic? As in, almost suggesting it's part of a car or something like that, right? That's not what it is. It is a collection of protocols. It's a suite, right, which is a collection of protocols. How many in there? Not just two, TCP and IP. It's a lot more than just those two. Hundreds of protocols. And of course, protocol itself, what is that? It's nothing but a standardized set of rules, right? You and I, by the way, are communicating right now using the standardized set of rules of English. That's why we can understand what, I will be able to understand what you're saying. You'll be able to understand what I'm saying right now. Without these rules, it won't make sense. Imagine someone gets into this webinar that doesn't understand English at all. They're going to say, what? I don't know. There was some bunch of noise going on. Someone was making sounds, funny sounds and strange sounds. Didn't mean anything to me. That's really what it is. So without the rules, it doesn't work. Now, some of the protocols are considered core, as in essential, main, so to speak. And that's TCP, UDP, IP, and so on, a bunch of other ones. But there are actually hundreds of other protocols, lots of them. And not all of them are used by all functions, all services. But the idea is that we're going to talk about some of the core protocols and some of the other basics we need to know. So this actually diagram illustrates the relationship between some of these protocols. IPv4 is the main protocol, right? Internet protocol, as it's called, IP, Internet protocol, and it carries most of our data. So we'll talk about that. But a lot of our data, for a lot of our applications, right, like HTTP, which we use for browsing, etc., are often used. Not used, sorry. They often are carried. The data of our HTTP is often carried in, or usually, not often, is usually carried in TCP, which is carried in IP. So that's how it works, and this is the relationship between them. So what is IP? So and again, if I ask you what's IP, I don't want to hear that it's Internet protocol. What you want to typically say is it's basically, it's the main protocol that carries most of our data. And version 4 is still the more commonly used one, right? Version 6 is still not as commonly used as version 4 is. So the idea here is that it is a routable protocol. There are other protocols other than IP that are not routable. And when a protocol does not have a network and host portion in the address, it often means it's not routable. So that's one of the things that makes it routable. But there are other properties too. It is connectionless. With IP, when two devices are talking to each other, they don't establish connection. IP just says, here it goes, and transmits it whenever it needs to. It's also unreliable, as in it does not confirm that the other side gets it or not. So that's one of the other big properties of IP that we need to be aware of. And the address for version 4 is 32 bits, the 32-bit address, which means we can't have as many IP addresses as we'd like, right? The world is effectively, for all practical purposes, out of IP addresses. So, that's one of the reasons why we've also started moving towards IPv6. But IP version 4 is still the predominant, the main protocol being used. And there are ways to overcome the lack of addresses as well. So this is what, now here's another big thing. If as a professional, as a technical professional, we need to understand these things really well, the idea is how do we understand the protocol really well? One of the ways to do it is to actually break down the individual components of the IPv4 header. And here are the various fields of the IPv4 header. Now, for lack of time, I'm not going to discuss these in detail today, but just want to give you a sneak preview, give you a heads up that this is the breakdown of the header. And the idea is that if we really want to understand the protocol, then we should understand the purpose of each of these fields and how they work. What are the typical values? That's what we need to be aware of, right? And again, by the way, if you need to troubleshoot TCP/IP, this is essential. This is not even optional. Right? Any network professional, I know I have used this amazingly, but it only works if you understand these details. So just keep that in mind. And that's how you understand the protocol. Similarly, what is TCP, right? So again, this is the IPv4 header. Like I said, various fields in here, right? We don't need to go over the details right now. But again, because of lack of time. In class, when I teach TCP/IP, we go over each and every field in detail. The students actually get to see these fields in the lab. When they do the lab, they see how these fields work, what are the different values, and how the different values affect the communications and whatnot, right? So that's the beauty. Similarly, if I ask you what's TCP, right? TCP is, again, I don't want to hear TCP's Transmission Control Protocol. That's what the acronym stands for, right? Even I know that, you can know that, you can look that up. But to really understand TCP, we need to understand, A, what it is. So it's actually a transport layer protocol. Yeah. So the transport layer protocol, that is connection oriented. Now TCP does establish a connection with the other endpoint. When two endpoints are talking to each other, they actually have to, using TCP, they will have to establish that connection before any data can be exchanged. Now, otherwise they cannot start transmitting data right away. So they have to, shake hands almost and establish that connection. Then once the connection is established, then they can exchange data. It's full duplex. That means both endpoints can transmit, receive simultaneously. Whenever either endpoint wants to send data, it can, and whenever it wants to receive, it can simultaneously. Reliable is one of the big features of TCP. So, it uses sequence and acknowledgement numbers. It actually confirms that the other end received this data. See, right now in this webinar, I cannot confirm whether you understood what I said or not. If I try to do that, there's 200 attendees. we won't get done until tomorrow. So the point is that TCP does confirm with the other side, did you get this data? And that's called reliable. And it uses sequence and acknowledgement numbers for that. There's also sender side and receiver side flow control. Both endpoints can say, hey, speed up or slow down, right? So speed up or slow down, and that's called flow control. So either endpoint, not either, but both endpoints can independently specify. So if you feel I'm going too slow, you can say go faster, prog. I can say, okay, I can go faster, but I don't want you to go any faster because I can't handle any more data at a time from you. So that's the beauty of that. And one-to-one delivery, right? So again, 2 endpoints only. One-to-one is that's what it means. It's not used for group chats. You cannot use it for group chats. And they use port numbers to identify applications. I'll show you what that looks like in a moment. Well, so actually going back, let me go back. See, here's this slide. These are the port numbers. So Telnet uses port 23, FTP uses 20 and 21, HTTP uses 80, we all know that, right? And so on. So these are the port numbers. So the port numbers in the header, notice, in the header of the TCP will identify. So source and destination port numbers will identify the actual application or protocol being used. So this is what the TCP header looks like, right? So these are the main TCP characteristics, and this is what the TCP header looks like. Once again, if you really want to understand how TCP works, you have to be able to understand each of these fields, how they work, what are the typical values, what are the normal values, what are the not normal or unusual values, right? And even the flags. Notice the flags, there's actually 8 of them in here. Again, I can't go over that in detail right now just because of lack of time. But the beauty is, once you actually understand this, you'll understand the protocol really well, right? So that's the idea there. And so, these are the various fields that TCP uses. It can actually have more using options, but this is the minimum TCP header layout that you have to be able to understand. Right, so that's the beauty of TCP. Now, TCP is the main protocol used to carry all our surfing data. Whenever we are surfing, HTTP, right, or HTTPS, net banking, whether you're surfing on Facebook or whether you're surfing on, CNN or ESPN or any of your favorite websites, whether you're using Gmail, you're using HTTP. And that is all carried, HTTPS, which is all carried by TCP. So that's a very critical protocol that we need to understand. Now, so what about UDP? Now, UDP, again, UDP, the acronym itself stands for User Datagram Protocol. But if I ask you what is UDP, you should not say User Datagram Protocol. You would say, you should say basically it's connectionless unreliable, or sometimes it's called connectionless best effort protocol. But it's, again, what kind of protocol is it? It's a transport layer protocol. So if I ask you, similarly, if I ask you what's TCP, you would say it's a connection-oriented, reliable transport layer protocol. Similarly, UDP is connectionless unreliable. Connectionless unreliable transport layer protocol. UDP, of course, also uses port numbers to identify applications, but it's much simpler. It's a lot less overhead. Well, when there's no connection that needs to be established, then it's not reliable. With UDP, there's no guarantee the other end will get it or not. UDP says, look, I tried. If they didn't get it, well, not my problem. Good luck. So that's the idea with UDP. And so because it's much simpler, it has less overhead, it's also a little bit faster. Now, and guess what? This is what the header looks like. Want to take a look? So here's your UDP header. Look how small it is. It's just 2222, 8 bytes of header versus TCP header, which when you add all this up, it adds up to 20 bytes. So this all adds up to 20 bytes in TCP header compared to UDP header, which is just 8 bytes. Much simpler. Source, destination, port, link, checksum, you're done. And again, this is laying the broader context, right? Here's typically your Ethernet header, or sometimes Wi-Fi these days. IP header, 20 to 60 bytes, what I showed you earlier. UDP, 8 bytes. Then the payload, this is the data. Same, this can be TCP or UDP header. TCP, of course, will have a much bigger header with 20 bytes. But then it's the payload. This is the actual where the data goes, right? So that's basically the idea here. Yeah. Now, again, these are all basics. If we want to really understand this TCP/IP as a protocol suite, we need to be able to understand the headers for all these protocols. Now, there's lots of other core protocols. Some of the main ones here are DNS, right? DNS, if you recall, will help us do what? DNS will help us translate the names to IP addresses. That's why you and I can basically type in www.amazon.com or globalknowledge.com, and it will load the website page or the web page from that website on our client, on our browsers. And the idea there is that it basically is what translates the names to IP addresses. At the end of the day, IP addresses are needed to communicate. Names are not helpful in communicating. It's only helpful for the human, for us. And the idea here is DNS helps us convert or translate the names to IP addresses. ICMP is what we use when we ping something, and it's also used for all kinds of error messages behind the scenes. You and I won't typically see the error messages, but behind the scenes, ICMP is used. HTTP, of course, is used for surfing the web, right? And HTTPS, that's implied. And then SMTP is what's used for email. FTP is used for file transfer. Telnet is used to log in to a remote device. DHCP to obtain IP addresses automatically. SNMP to manage IP addresses, not IP addresses, sorry, manage devices in network management. SNMP is used for that purpose. ARP is used to, again, translate IP addresses to MAC addresses, right? And so on. Real-time transport protocol is used for voice or IP, and so on. So these are some of the, but not all, some of the core protocols that are needed for lots of the other functions. And as you can see, it can get very complicated, right? To get a really good understanding of TCP/IP, we need to understand many of these in detail and understand their headers. And again, with experience, as your knowledge increases, you become more confident, you become more efficient in solving problems, in troubleshooting these things. So that's the idea behind understanding these. Now, one of the other big things is routing. In fact, routing is very essential and important to understand because oftentimes when networking professionals are troubleshooting problems, routing is blamed when security is a problem, or security is blamed when routing is a problem. So it's very important to basically understand what routing is and how it works. In general, routing is basically nothing other than forwarding traffic towards the destination, right? Yeah. So imagine if you're trying to go from London to New York. From London to New York, you want to make sure you start flying in a west direction, right? But if from London, if you want to get to New York and you start flying east, you know you're getting in the wrong direction. Well, eventually you'll get to New York, but you'll run out of fuel typically before that. So that's the idea. Routing is just that. Right? Routing is the idea behind routing is that it's basically forwarding data towards the destination. So most of the routing is based on the destination and forwarding it closer to the destination. So here you have these various lanes that are connected to each other through a very complex, or not very, but somewhat complex wide area network, where there are multiple paths multiple ways to get from any LAN to any other LAN. The idea here is that these routers, these are the little circles with arrows, are routers. They're making routing decisions. They're making routing decisions on how to forward the data in the most efficient and the fastest or best way possible towards the destination. But so routers make these routing decisions, and again, there's a lot of details to routing that needs to be understood. So the idea there is that how do we understand some of the details or specifics of routing is very important. And how routers learn about different networks and different ways to get there, right? Think about it. If you want to go from one city to another city, usually there's lots of different ways, lots of different roads to connect these two cities. But there's oftentimes one road that is the most efficient. That'll get us there the fastest, right? It'll get us there the shortest distance. So it's important to be able to understand these different ways. Routers learn about how to get to the destinations and how they make their decision. So all that is part of routing, and it's very critical. And what's amazing is that on the internet it works. When you type in www.amazon.com, you know that the website is coming from some other server many routers away. There's lots of routers separating us and that website, but still we get that web page immediately, right? So routing is working amazingly well, but again, it's taken time to get to this point, to get this fast. And routers are doing some amazing stuff in the background. We don't even realize it. So that's one of the big things there. How do routers make their decision? Right? The idea there is that routers have what is known as a routing table. Now, routers use different technologies to build their routing table. And the routing table, by the way, each of these routers has their own routing table. And in the routing table is a list of destinations, list of destination networks, and what is the best way to get to them. Only the best way to get to them is put in the routing table. Routers actually, so each of these routers knows multiple different ways to get to all the different destinations, but only the best path only the best path is put in the routing table. So then when the router receives a packet for any particular destination, it checks its routing table and says, do I know how to get to this destination first of all? And there are three possibilities. Either the router has no routes to the destination, in which case the packet is dropped and the router will report that destination as unreachable. If the router has only one path to the destination, it'll use that route and the packet is forwarded, it's done. The router is done with that packet. But if the router has multiple routes, then it becomes a challenge. Now the router has to check the different routes for that destination and then make a decision on which is the best path. And it's usually based on something called longest bit match. Again, I don't want to get into the details right now, but certainly, when we discuss this in our classes, we go over some of the details and specifics of how it figures out what is the longest bit match, and then it uses the lowest metric. Now, what is metric? Of course, metric is nothing but a unit or measure of how easy to reach or hard to reach a particular destination is. There are lots of different types of metrics that can be used. Just like if we want to measure distance, right? We can use inches, centimeters, meters, kilometers, light years, right? If we want to just measure the distance from the Earth to the Moon or Earth to the Sun, we measure it in light years or something along those lines. We don't measure it in inches. We don't measure it in centimeters. We may measure it in kilometers, right? But it's still not as efficient. If you want to measure the distance from Earth to Jupiter, right? You definitely don't want to use feet or meters. You want to use light years, something along those lines. So these are the different kinds of metrics: hop count, bandwidth, right? Where you literally identify which path has the best bandwidth or which path has the fewest hops. Or again, routers can arbitrarily have some path costs designated for different links. And it's not too commonly used, but reliability, delay, and load can also be used, but it's usually not as effective in helping routers make an efficient decision on how to forward data. Right? So that's what it is. Routing protocols is what routers use to talk to each other. So all these routers in this diagram will exchange some routing information using routing protocols. What are some of the popular routing protocols? OSPF and EIGRP are some of the most popular routing protocols, but you also have other ones. On the internet, BGP is used between providers, between providers and customers. But in internal networks, OSPF and EIGRP are the most popular ones. RIP is one of the original routing protocols, not as efficient. And it's older, more simple, it has more limitations. Right? But that's the idea behind that. Bottom line, see again, these links, notice this is only 10 megabits per second. This is 155 megabits per second. These are gigabit links. Notice from LAN A to LAN B, the fastest path is going to be along the gigabit link path. If your metric is bandwidth, but if your metric is hops, then the fewest number of routers to go through would be through this path, right, with just 2 hops. But notice this has only 10 megabits per second of bandwidth. This has 1,000 megabits per second of bandwidth, which is 1 gigabit, right? So obviously this path is usually going to be faster for larger amounts of data. So that's the bottom line. And routers can distinguish between these paths if they are using bandwidth as a metric. But if they're not using bandwidth as a metric, they won't be able to distinguish between the paths. And if they're using hops, they'll think the bottom path is the best. But routing protocols help routers figure all this out. And that's the beauty. Now, so remember again, the idea behind this is that basically we have IP carrying data for all the applications. An IP typically will have either TCP or UDP in it. And the data will be carried in TCP or UDP, which will then be carried in IP and then in Ethernet or Wi-Fi, and then it's transmitted. So that's how it all ties in together. But again, these are all the TCP/IP protocols. Notice EIGRP, OSPF are routing protocols. They operate at the internet layer. TCP, UDP operate at transport layer, and these are the application layer protocols. It's important to understand that distinction as well. IP addresses themselves, of course, are going to be, with version 4, 32 bits. Notice there's a network portion and a host portion. It'll vary, of course, depending on the address. But that's also partly what makes it routable. And here's one of the other big things. I apologize, I forgot to mention, right? With routing, if I ask you what is routing, you will also say it's forwarding data from one network to another. That's what routing is really defining, going from one network to another. If you're trying to go from one network to the same one or inside the same network, you don't need routing. A switch will get the job done. Routers will help you get from one network to another. So that's one of the big things there. And when the address has a different network portion, you can identify the different networks. And that's how routers know, okay, you're trying to get from this network to that network. So that's how I'm going to forward you. Right? So that's where it is. And of course, actually, it's a 32-bit address, 32 bits, ones and zeros. But we humans cannot deal with 32 bits at a time easily, so we convert it to dotted decimal. We convert each block of 8 bits to a decimal value, separate them by dots. That's why it's called dotted decimal notation. Right? And within that, some portion may be network, some portion may be host, and so on. Now, one of the other things is, besides the network and host portion, a third tier is added for subnetting to make it much more manageable and to reduce the address waste. So the idea there is that subnetting was introduced to achieve these goals. And the way we subnet will be determined based on how many broadcast domains or how many networks do we need, how many host addresses or IP addresses do we need, what is the total range, what's the potential for growth. Will we grow the number of networks or will we grow the number of hosts? And depending on that, we'll subnet accordingly. Right? Now, just so you know, by the way, when I teach subnetting in class, I take at least 4 hours to teach it. Why? Because I insist we know the binary. So before we can understand subnetting, what all do we need to know? First of all, why do it? What is the purpose? And in a little bit more detail than I just mentioned here. But then we also have to know the binary numbering system, the ones and zeros, how they convert to decimal, right? We got to do that. I insist students know that. I give them homework for it. We have to understand the IP address classes, A, B, and C, and the octet boundaries. Each of the 8-bit blocks is called an octet. We have to understand what subnet masks are and the rules, how they work, what they do. And we have to understand how many bits will determine how many host addresses we'll have. So that's typically laid out in a table or subnets. Number of host bits or number of subnet bits will determine how many hosts or subnets we'll have. That has to be understood. And we have to be able to count the bits in an address. How many network bits, how many subnet bits, how many host bits do we have in an address? And even the prefix notation. You know, when you see the subnet mask written as a /16, /24, you have to understand what that really means and how it works. Unless you understand all of this, guess what? You're not going to be able to understand subnetting. So to teach all this, to teach subnetting, I have to teach all this, and that takes a while, right? So here the example I like to use is subnetting is like slicing pizza. When you haven't sliced the pizza, when the whole thing is intact, it's like having one bigger network, not necessarily big, but bigger. When we slice the pizza, each slice becomes the equivalent of a subnet. They're just showing one here, but typically we'd have more than one slice, right? So, but that's the idea. So the slice is the equivalent of a subnet. The whole unsliced pizza is the equivalent of a network, right? So that's the gist of that. And finally, IPv6, because we have effectively run out of IP addresses, so we can't have any new ones. We can use the existing ones, and we are able to manage okay with the existing addresses if a country and a company and an organization has those. But if they don't and they need more addresses, then there's no choice but to go to IPv6. IPv4 addresses are 32 bits large. IPv6 addresses are 128 bits large. It's huge. Partly done to make sure we never run out of IP addresses again. Right? Also partly done so we can have more levels of addressing hierarchy, or we can also assign addresses without worrying about running out and without worrying about not having enough right now and running out even in the future. So with IPv6, one of the other big things is the header is simplified. If you recall, the header in IPv4 had quite a few fields. They actually reduced the number of fields in the header in IPv6. And as a result of that, you might say, well, does that mean they took away some of the functionality? And the answer is basically no. They added what are called extended option headers and extensions, basically. Options and extensions were added to give us a whole bunch of additional functionality, but it's taken away from the basic structure. They've actually given us more functionality than we used to have in IP version 4, but it's not required for all devices to process that or handle that. They're added as extensions and options. So you have authentication extensions, you have encryption extensions, and you have various other optional encoding. Quality of service is still maintained like we used to have, better multicast support, better security support, because IPsec has been added to IPv6. And addresses are now assigned only by region. Earlier they were assigned randomly. Now addresses are assigned based on region, so that's what it is. And you know, there's also a transition plan to migrate from IPv4 to IPv6. So it's not easy, it's not trivial to go from one to the other. The two protocols are not compatible, by the way. IPv4 and IPv6 are not compatible with each other, right? So when you move from one to the other, you're basically going to, you can't talk to, IPv4 device cannot talk to IPv6 directly. So that's why you need an incremental migration plan to transition over. So that's the gist of TCP/IP, guys, in a very short nutshell. Now, again, you know, I take a week in the TCP/IP class to teach all this, right? And students get to do labs. They actually get to practice this and see it actually working. They see that not only demo, they actually get to do their own labs and they see how this works. They get to change different things and see how that affects connectivity and communication. Kind of neat stuff. So I had to share some jokes with you guys, and I'll let you read them. I won't read them out loud. Let me know what you guys think. Put in your comments in the chat window, and feel free to share what you guys think about this. Now, I'll give you a minute or so to read it, and then we'll go to Q&A.
Thank you so much, Prad. That's awesome. I'm reading through these. Folks, as you're reading these questions, as you're reading these jokes, be sure to put all of your questions for Parag into the Q&A section of the control panel. Just a friendly reminder, this recording will be provided to you in about a week. We do not offer a certificate for this webinar. It would basically just be like a participation ribbon, so we don't do that. Anyway, so any questions you have, put them in the control panel in the Q&A, and Parag, if you're ready, we'll go ahead and get going with these.
Yeah, sure. You want to start? Yeah, just read out the question and.
Yeah, I'll read out the questions. I'll start here at the top. And
yep.
Folks, if you see a question in the Q&A and you want it answered, be sure to give it a little thumbs up, and that way it'll bump it to the top and we can make sure we get to it. And again, I see some questions coming in through the chat. Please put those in the Q&A section. That way we can get it answered for you, Michael. Okay, so first question here. What are some best sources to learn TCP/IP foundations? Oh, sorry, got bounced down here. And even networking in general.
Okay, so excuse me, sorry. So the idea is that, you know, the best way to learn this is ideally in an environment where you can learn the theory and the practice, both the practical aspect of it. So, you know, you can read books about it. That's definitely one way to do it. I remember I actually took a semester-long class. One semester-long class in a community college more than 20 years ago on TCP/IP. Back then, it wasn't as popular as it is today. It was tough learning, but you know the thing is, there I did not get the practical aspect of it. It was more theoretical, and we spent a semester on it. These days, that's why Global Knowledge offers these classes. It's very popular, and I love. In fact, I'll tell you. And I'm not trying to show off. I'm not trying to just market our classes, but I actually feel confident that a student will learn more in a week-long class on TCP/IP, and we have another class called Understanding Networking Fundamentals. In those classes, you will learn more in a week than I did in a semester when I took this class, because we explain the theory. We break out the header. I explain the purpose of each field of the header, and then you guys get to do labs on it and see how it actually works. That will make it understand. That will make it click for you guys much better. That's the best way to learn it. You know, you can make up your own labs potentially, and you can read the theoretical books. But you know, also having someone who can explain this to you, having someone who can clarify your doubts, your questions right there, while you're learning, while you're practicing the labs, while you're doing labs. I'm not off playing, you know, solitaire. I'm in there answering questions, helping people understand what's going on. So that's. To me, I think that's the most efficient way to do it. I hope that helps.
Fantastic. Okay, next here, what is IP4 and IP6?
It's IP version 4 and IP version 6. By the way, IP version 4 was developed almost half a century ago. I mean, you know how you and I want the latest and greatest smartphone, latest laptop or tablet? Well, guess what? We may have the hardware, but that's latest and greatest, but the protocol we're using is half a century old. Some of you were not even born back then, right? When this was developed. I was, but you know, obviously, I'm not using that. Yeah, but the thing is, most of us are using IPv4. IPv6 is a newer version. But unfortunately, not everyone has migrated to it. And it's not necessarily right away, but that's where it is. Yeah. Yeah, so that's IP version 4 and IP version 6.
Thank you very much. I did see a question come through again about the recording. It'll be provided to you in about a week. It's just a recording. We do not provide the slides, the decks for you. Okay. How's flow control achieved in UDP?
It's not. With UDP, there's no flow control. It's basically, if you can't handle it, well, then too bad for you. Literally, that's what it is. And that's what makes UDP much simpler, more efficient in a sense, and faster. But TCP manages all that. And TCP says, whoa, slow down. And the other end will honor that. If one end of the TCP session will say slow down, the other end honors it. With UDP, it's pretty much here goes, hope you're listening, hope you get it, hope you can handle it. Boom. That's the difference between these two protocols.
Gotcha. All right, next question. Is it possible to have a low-cost congested route and high-cost route with no traffic? How does routing algorithm choose between the two?
Very good question. And by the way, the other questions were also very good. I apologize. I didn't mean to suggest they are not. But this is a slightly more advanced question, which is great. So here's the thing. Congestion is not factored usually in the routing decision. For routers to factor congestion, somewhere down the road, by the way, especially, is a considerably more advanced function. In fact, some of that is done through software-defined networking now. But again, that's a very advanced, very complex topic. It requires much higher degree of coordination between routers, and basic routing simply can't handle it. But more advanced routing capabilities can, and even, like I said, software-defined networking can do that. Yeah.
Very good. Why is IPv6 still not adopted even though it has better features?
Another very good question. In fact, the DoD has had a deadline to migrate to IPv6 since, I don't know, maybe a decade or so or more. But it's not a trivial transition. It's a fairly big deal to transition or migrate from v4 to v6. So then the question is the pain of living with IPv4 greater, or is the pain of migrating to v6 greater? So for many organizations that have not migrated, the pain of migrating is greater, so they're okay with using IPv4 for the time being. Eventually they'll all migrate, but who knows? By then IPv8 might be out, But that's the big reason, because it's not trivial. It's not like something you can't just say, okay, let's migrate and do it over a weekend. There's a lot more involved in that, depending on the size of the organization, right? Depending on how complex your network is.
Very good. Oh, I like this question because I'm a marketing person. What class is this that you mentioned, and where do you teach?
Brent, you want to answer that, or should I?
Go ahead, man. Go ahead.
All right. Thank you. You'll probably do a better job of answering than I will, but let me try. The class that is mentioned is called TCPIP Networking. It's a 5-day class. I teach that regularly. I love teaching it because it gets into the basics. And I like teaching the basics because sometimes I get students in advanced classes who don't know the basics, and then they're lost. So here I get to teach them these things. Like I said, I spend more than 4 hours teaching them this subnetting. All the basic stuff on subnetting is taught there. And then we also teach lots of the other things. We break out all the headers and all that. But the TCPIP networking is a 5-day class that Global Knowledge offers. And believe me, I'm not exaggerating. I'm not doing this for marketing purposes. I literally think students learn more in that 1 week than I did in a whole semester. So, we have another class, by the way, just to pitch, another class called Understanding Networking Fundamentals, which also I love teaching it, right? Because it teaches you the basics of switching, routing, TCP/IP, subnetting, which students don't know coming into advanced classes. When I used to teach Cisco classes, students wouldn't know those basics. And you couldn't even pass a CCNA without knowing those things, so yeah. That's
very good. And I'd like to point out that I did not coach Parag in any of that. That's all right at the top of his head. So appreciate it.
Yeah.
Appreciate that. Okay. Next question. Are those protocols used in a cloud environment, or have new protocols come into existence?
So, TCP/IP is used in a cloud environment too. The cloud often has some other proprietary protocols as well. But at the end of the day, to communicate at least with the edge of the cloud, with the periphery of the cloud, we typically do it through the internet. For that, it's pretty much just TCP/IP. Inside the cloud, they may have other proprietary protocols and whatnot, right? But customers talking to the cloud is still done over the internet, so therefore it's TCP/IP.
Very good.
Yeah.
Okay, next question here. Generally, what does the port mean?
You have the port of New York, and you have no, port here is the reference number that helps us determine, helps devices determine which application to send the data to. Right? Remember, on a single laptop, we are using email, we are using a browser, we are surfing over to lots of websites, we are using email, we are chatting, we are using maybe a voice or IP call, database, all kinds of stuff. Well, all the data is coming into the laptop from the single Wi-Fi or single wired Ethernet connection. How will our laptop know which application to send the data to? And that is determined by the port number. So when the port number is included in TCP and UDP, the laptop or the device, when I say laptop, I mean any device, right? It could be an iPad, could be a cell phone. But the device will then say, aha, this port number is sent it to this application. This port number is sent it to that application. That's what the port number means.
Gotcha. Okay, what is the best method to learn to do subnetting in your head?
It's math. But along with the math, you need all the rules and practice. So like I said, in fact, if you do the homework I assign, and if you do the prep work and you really understand, how to do it, then with a little bit of practice, you can do quite a bit of it in your head. It's not that difficult. But again, the students often try to take the shortcut, and their shortcuts don't work. They flat out don't work, right? That's why when I teach subnetting, I insist on teaching the binary. I give homework. I don't grade. I don't collect the homework, but I insist they do it if they really want to learn it. Then the students who do the work can do some of it in their head, and it's pretty cool. It's really nice. I mean, it gives you a really good feeling that, okay, cool, I could do that.
Okay, and what class do you teach subnetting?
Both TCP/IP and understanding networking fundamentals. In both the classes, I teach that, and we spend a good bit of time doing it.
Very good, very good. We have a few questions here too. People asking about upcoming webinars and past webinars. So I will put the links to upcoming webinars in the chat, and also a link to past webinar recordings in the chat as well. Okay, how does DNS use both TCP and UDP? Excellent
question. DNS uses TCP and UDP for different functions. When you and I type in www.amazon.com, our device will send a query, a DNS query, to say, hey, DNS server, can you resolve this name to an IP address? That uses UDP. When two DNS servers talk to each other within an organization, they use TCP to exchange the DNS database and DNS records. So different functions of DNS use TCP or UDP. That's how it works. But interestingly enough, they both use port number 53. But it's different protocols, so there's no confusion. Good question.
All right. Next, how does classful and classless become compatible if both are used in networks?
All right. That's a slightly advanced question. I'll see if I can give you a brief answer to it. It may not fully answer your question, but let me try. Classful addresses basically use their classes A, B, and C. Yeah. Classful addresses A, B, and C is what is referred to as classful, where the class matters. Classless means it does not matter. Now, classless addressing is often used in routing and some other functions as well. With classless addressing, it says, look, don't care for the class. Here's an address. Here's a mask. Just do it. Right? So they can coexist, especially when you use classless interdomain routing. versus, for subnetting or whatnot, you typically still do use classes in some way, shape, or form. But like I said, to give you a more complete answer, we would have to get into far more details than we can right now.
Gotcha.
And that's why it's important to understand the basics as well. Sorry. Okay.
Yeah, no worries, no worries. And we had someone ask again, I need to understand more on ports, where I can get further information on ports.
Well, the best information is to read the RFC for it, or not for it, but for UDP and TCP. But a lot of TCP/IP information can be obtained on the internet. Just if you Google it, you'll get some videos on it and whatnot. So yeah, that's the general thing. I mean, yeah, understanding ports by itself is not of as much value as how it relates to in the protocols also. So that's what it is. Right? Understanding the protocols will help as well.
Very good. So we'll take two more questions here. So we have one asking which books, and I'm assuming they're meaning, what are some good books for them to check out to learn more.
Oh, geez. I used to know this. I don't know offhand. I think, personally, search on Amazon today and just pick up some books that maybe you feel have the highest reviews or, best ratings. I can't remember the name of the book. I own some books on TCP/IP, but right now, I'm really sorry. There are some classic books, if someone says some names, I might be able to confirm it, but unfortunately, I don't. Sorry, I don't remember the names right now. It's been a while. Tannenbaum is good for general networking. Good. Tannenbaum is definitely a classic on general networking, but not TCP/IP specifically. Maybe there's an author named Black, but I'm not 100% sure. Tannenbaum, definitely, I have that book. Yep. All right.
All right. And we'll do one more question here. So the next one down. Can we learn more about networking through online resources? Yeah.
Yeah, sure. I mean, you definitely can. Of course, there are lots of good resources out there. Lots of YouTube videos and whatnot. Like I said, but the challenge there is make sure, again, that you have someone else who can explain things to you, who can clarify your doubts, because otherwise you'll eventually learn it. It's just so much more efficient to have even a mentor who can guide you, who can basically who can clarify your doubts. That's the biggest thing, right? Okay. I think
very good.
I may also need to wrap up.
Yeah, no, I'm with you. Greg and Prag, we really, really appreciate your time. It's so fantastic. And I know we have a few questions that are still kind of outstanding. I would encourage everyone to reach out to Global Knowledge through some of our social channels, whether that's Twitter, Facebook, LinkedIn, Instagram, whatever it may be, make our social team earn their money. If they don't have the answers immediately, they will be able to put you in touch with someone who can get those questions answered for you. So again, Prag, thank you again for joining us today, and I hope everyone enjoyed today's webinar. If you'd like to learn more about this topic, we recommend the following course you just saw on your slide there. As an attendee of today's webinar, we'd like to make it easy for you to take the next step. So if you use these discount codes, you can receive 25% off your next Global Knowledge course. Again, we hope you will continue to visit the Global Knowledge website to access additional free resources like technical articles, white papers, and webinars. And I put the link to both of those in the chat there. So happy hand washing, everyone. Stay safe and have a great rest of your day. Thanks again, Prag.
Thank you, Brent, and thank you very much, participants. I'm sorry this is not more personal, just because we had 200 some participants, but I appreciate you guys joining us, and I wish you all the best. I hope you guys continue your learning and keep growing technically, and good luck. Yeah. Thanks again for attending.
Yeah, thanks, everyone.